Hello, sir. We are here to present our Cse106 data structure and algorithms mini project. Our topic is verify empirical time complexity of binary search. I am Abdulaziz Mahtab, and with me are Sheikh Mohammad Araf and Taj Mohammad Bhuiya. Our main goal is to compare the theoretical time complexity of binary search with its actual execution behavior. The main purpose of this project is to connect the theoretical concepts of data structures and algorithms with practical implementation. For our project, we focused on measuring the actual execution time of binary search for different input sizes. We then compared these experimental results with the theoretical complexity of O log n. So our main question was, does the actual performance of binary search support its theoretical logarithm complexity? Binary search is a searching algorithm that works on a sorted array. The main idea is very simple. Instead of checking every element one by one, binary search checks the middle element and eliminates half of the remaining search space after each comparison. Because the search space is divided by 2 repeatedly, the number of operation grows logarithmically. The best case is O1, while both average and worst case is O log n. Now I'll hand over the presentation to Sheikh Mohammad Araf, who will explain our experimental methodology and implementation.
Uh, Thank you, Abdulaziz Mahatab. Now I will explain how we conduct our experiment. We tested binary search using 5 different array sizes: 10,000, 20,000, 13,000, 14,000, and 15,000 elements. For each array, we generated random integers and sorted them using quicksort. Then we performed 1000 binary search trial for each array size. To measure exploration time, we used the getTime of day function, which allowed us to measure the time in microseconds. Finally, we calculate the average explosion time for each input size. Uh, then implementation workflow. Our implementation follows a simple process. First, we generate a random array. Then we sort the array because binary search requires sorted data. After that, we started the timer. We perform binary search 1000 times. Then we stop the timer and calculate the average execution time. Finally, we compared the overserved performance with the expected logarithmic behavior. The binary search function repeatedly updates the lower and upper boundaries and calculates the middle position until the target is found or the search range become empty. Then the next slide, empirical result and interpretation. Interpretation. From our experimental results, we observed that the explosion time remained nearly constant even when the input size increased. There were some small fluctuations in the measured time. These fluctuations can happen because of factors such as CPU catching and operating system scheduling. However, the overall trend strongly support the theoretical O-log complexity of binary search. Now I will hand over to Taj Mohammad Bhuiya for the verification and conclusion.
Thank you, Sheikh Mohammad Araf. Now let's compare our theoretical expectation with our experimental observation. Theoretical, Theoretically, binary search repeatedly divides the search space into half. Therefore, even when the input size increases, the number of comparisons increases very slowly. You can see our experiment showed us similar behavior. We tested input sizes from 10,000 to 50,000 elements with 1,000 trials for each size. The average execution time remained nearly constant with only minor fluctuation. Therefore, our experimental results provides evidence that the practical behavior of binary search is consistent with its theoretical O-log and complexity. The final conclusion was to our experiment successfully demonstrates the practical efficiency of binary search. As the input size increases, binary search does not require a proportional increases in the number of operations because it constantly reduces the search space by half. The measure execution times remained nearly consistent, while small variations were caused by small system-level factors such as CPU caching and operating system scheduling. Overall, our experimental results support the theoretical O-log and time complexity of binary search. This shows why binary search is highly efficient for searching large shorted data sets. Final, thank you. That concludes our presentation. Thank you, sir, for listening our presentation.